Okay, so today we're going to talk about potential temperature, which we hinted at before. Um, it's a concept that is used to make thinking about temperature in the ocean easier by relating temperature to other thermodynamic principles like entropy and energy and all that sort of thing, so that rather than having an equation for energy, which is quite complicated to understand, or an equation for entropy, which is extremely complicated to understand, we have just an equation for temperature, and that's what we evolved. And so if you remember last time from our energy budget equations, we saw this transport of energy from place to place on the Earth as being a useful concept for how the Earth played a role in the climate system. What does that mean in terms of the temperature of the ocean? So maybe you could think of this as warm water, which has more energy uh, per unit mass at the same salinity and pressure being transported towards the pole, and colder water coming back, and that would transport energy like that. But it's not quite as simple as that, because if you compress water, it changes its temperature, or you contract. So what if it went in a little bit deeper at higher pressures, or a little bit less deep at lower pressures? You wouldn't easily be able to figure out what the energy content of the water was per unit temperature. Similarly, we talked about all different kinds of air-sea fluxes that had different uh, impacts. How do these energy fluxes impact on the temperature of the water? So if radiation arrives, it's going to warm up the water, but how much? What's the temperature change that's related to that? And latent heat is particularly complicated, because latent heat is the one that relates the changes of state of water, like freezing or boiling. And so that one has a separate energy content. So we're going to talk a little bit about all these pieces today, and then we'll have enough of a basis to move on. I will say there's a lot more to learn about this. This is probably a whole class, semester-long class worth of information to think about this in both the atmosphere and the ocean. This is just a light summary. The new book, Vallis's Atmospheric and Oceanic Fluid Dynamics, the second version, really has a nice treatment of that I'm going to draw on very heavily today. So we'll see a lot of slides from that book. I'm trying to get an electronic copy of it available through the library. It's about 10 pages or so. That's a reference for you. But I also have selected a few bits from that book, a few of the key equations from that book in the format, because I think it's quite easy to understand, or more easy than other formats. And one of the things that's going to be of interest to us is this time scale difference between the time scales of the atmosphere and the time scale of the ocean. This has a lot to do with how rapidly the temperature and then the density responds to the amount of heat being exchanged, or amount of energy being exchanged. If you warm up the air, it expands, and then it can rise because it's lower density. Or if you warm up the ocean, it expands and it can rise. So the relationship between the density changes that are driving motion, the temperature changes, and the energy changes is a key part of how geofluids move. Okay, so to conclude, the conclusions we had from our global energy budget last time were that the motions of the atmosphere and the ocean are part of the meridional redistribution of heat. The ocean overturning gyres and atmospheric cells all contribute to that process. And estimating both the air-sea fluxes and the fluxes within the ocean is tricky and important. Okay, so to stay on this kind of broad theme of things being interesting, that are interesting, Earth is special in part because water is special. So water, the chemical water, has many properties that are intertwined with the Earth system and life on Earth. It's the only substance on Earth that's in gas, liquid, and solid form. It has an enormous heat capacity. Heat capacity is the amount of energy stored per unit temperature change. We'll come to that in a second. Water varies in density. The oceans are stratified in density, so less dense water at the top, more dense water at the bottom. Most of the pressure variation in the ocean is hydrostatic. We're going to talk a lot about that in the next lecture, but we'll hint at it a little bit here. It basically means that the pressure increases with depth when the water is not moving. But first, we're going to talk a little bit about seawater's heat capacity, equation of state, and chemistry. The heat capacity, as I said, is the amount of energy required to change a unit of temperature. The equation of state is an equation that relates the salinity, temperature, and pressure to the density that results. Or it could alternatively be for other thermodynamic variables like entropy or enthalpy, or we'll see a lot of crazy ones. A little bit about the chemistry. So for the physical chemistry of water is largely a result of hydrogen bonding. So this is the water molecule, the two hydrogens are pinched off on one side and the oxygen is left on the other. So it's extremely polar. The positive charges and the negative charges are very unevenly distributed over the molecule itself. So the molecules next to each other can bond, not fully, but hydrogen bond, which means they're attracted to one another. So the oceans can transfer large amounts of heat with the temperature change due to water's high heat capacity and high latent heats, which are both the results of this hydrogen bonding. There are also colligative properties that have to do with the fact that seawater has other stuff in it other than water. Seawater density is affected by temperature, but also salinity and then pressure. The ocean is stratified by density. It is also stratified in pressure. It is also stratified in salinity and temperature to some extent, but really only pressure and density are monotonically increasing as you go from the surface to the abyss. Temperature and salinity can sometimes be inverted so that they are not increasing with depth. The static stability is something that we'll see is derived from a concept of the potential temperature or the potential density. And the static stability says if you had dense stuff on top of light stuff, so not stratified by density, it would actually overturn. It would be unstable. So the fact that the ocean is stratified by density from light to dense means that it is stable. The other interesting thing that comes out of this whole story is that the light and sound penetration of seawater has a lot to do with these properties. The sound speed in particular is a function of the temperature, salinity, and pressure. And the last piece about chemistry that you might think about is, what is this salinity? What are the salts that tend to be in the ocean? Well, sodium chloride is the most common and also the most widely known. There's lots of other stuff that really counts as a salt, including forms of carbon that are in the ocean count as a salt. And so the pH of the oceans is a rather complex result of all of those salts that are buffering and addition of acids and bases of lots of different forms, which is something we'll talk about later when we talk a little bit about ocean acidification. Okay, so let's focus a little bit more on sensible heating and heat. So the sensible heat in one particular unit is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree centigrade without changing the phase. So for that there are two different forms. There's the form that depends on the amount of the quantity, which we typically denote with a capital CP. So the sensible heating, or the amount of energy, is related to the temperature with this specific heat. The specific heat, this is the specific heat of the total substance. And then the small c is the specific heat of the substance per unit mass. So you pull out the mass separately. So if you have more stuff, the mass is greater. It takes more energy to heat it at the same temperature. That makes sense. If you have less stuff, it takes less energy. If you want to heat it more than 1 degree, you have to put in more energy. And this specific heat is not exactly a constant, but it's not something that varies as too much. So, well, actually, if you look in the Valis book, there's a discussion of how you can extract predict the sensible heat from other parameters of the ocean thermodynamics, but for our purposes today, it'll be easy enough just to take it as a constant. Liquid water has a higher specific heat capacity. So specific heat capacity is the little one per unit mass than almost any other substance, 1 calorie per gram per degree C. Water vapor and ice are about half that, so only half a calorie per gram per degree C, and that's because the hydrogen bonds in the liquid are much stronger than they are in either the gas or the solid form, which is doesn't allow the water molecules to bond to each other. See, here's the hydrogen being close to an oxygen, that's the hydrogen bonding. And air, dry air, has only about 1/4 of a calorie per gram per degree C. So if you put water vapor into air, you actually are raising the heat capacity of the air. It takes more energy to warm moist air than it does to warm dry air. And so hydrogen bonds inhibit the speed, and that's so when you put in energy, the molecules start moving faster. But because of the hydrogen bonds, those molecules are held together more tightly. And so when we think about the temperature and the energy that represents, the hydrogen bonds are key in thinking about what sets up the specific heat capacity. All right, so calories are a weird unit of energy. How do we get to energy that we've been talking about so far? Things like joules per second or watts. We've actually been talking about watts per meter squared of energy flowing between different reservoirs, or petawatts of transport from pole to equator. A watt is a joule per second, and a joule, or 4.816 joules, is a calorie. So a calorie is a convenient unit for water because it's defined to be 1 when we're talking about liquid water. But actually what we should think of is 4.816 joules are required of energy to warm 1 gram of water by 1 degree Celsius. Latent heat is the heat that comes out of the closet when you change the phase of water. The one common form you might think of is how much energy does it take to melt ice. So there's a latent heat of fusion, which is about 80 calories per gram, that goes into the melting of ice. That's also higher than almost any other substance. If you start out with ice that's colder than the melting point, you first have to warm it up to the melting point. Then to melt it, you have to apply this 80 calories per gram. Then you can warm in the liquid phase. And we'll talk a little bit about this. Ice can also sublimate, which is where it forms directly out of the gaseous water vapor form. Okay, what about the energy of vaporization and evaporation? It's a different latent heat. So the latent heat of vaporization is really big, 540 calories per gram. So this is when we vaporize, is when we make water vapor out of liquid water. And so it's 540 calories per gram. So we talked a little about the fact that the latent heat was the primary way that the atmosphere and ocean exchanged energy. It's because this latent heat of vaporization is so big that is such a powerful piece. So for every gram of water, it has 5.5 times as much energy as the difference between 100 degrees C water and 0 degrees C water. So that's a huge difference in terms of the amount of energy. So when water molecules evaporate from the surface of the liquid, they require this extra piece. So if you were to try and boil water from 20 degrees C, so typical ocean surface temperature, it would take 585 calories per gram, 540 to do the evaporation, and the other 45 to get from 20 up to closer to boiling. Let's talk a little bit about how that might work. So if you imagine putting in heat down here and the resulting temperature, if you start with very cold ice and you warm it up to the freezing point, that takes, this is a relatively steep slope because the heat capacity of ice is not that high. Then you apply the heat to take up the latent heat of fusion, 80 grams per calorie to make this part. And so now if you had started at 0 here at negative 40 C ice, by the time you put 100 calories into that gram of ice, you would only have reached 0 degrees, which is a lot more than you might think. Then the next 100 calories would warm you from across all of the span of temperatures of liquid water, getting you up to 100 degrees C. And then the next 540 calories you applied would be required to evaporate. And then only then would you be heating the water vapor over here. So if you want to go from cold ice up to water vapor at 140, you're talking about 800 calories. So in stages. And you can't jump one of these stages very easily. You can very briefly supercool or superheat across one of these phase transitions, but frequently, but you can't usually go very far. So as you go back and forth in energy, you have to handle both the latent heating and also the sensible heating. Sensible heating is the heat that can be sensed by temperature. So this has a lot to do with the temperatures that we see between the seasons from place to place in the oceans versus on land. So you can see that the land temperatures are changing a lot with the seasons coming and going, whereas the ocean temperatures are actually not changing that much. In fact, this is even a smaller color bar than this, so it's not even fair to put color by next to color like this, because the ocean sea surface temperature only goes down to -2 rather than -25. What does that tell us? Well, it tells us that the higher heat capacity of the surface of the ocean is really resisting the temperature change with the seasons as the sun is changing its intensity. Okay, so now we want to talk a little bit about the equations of motion of a fluid, and we've talked about the conservation of mass. We will talk about, we talked about the conservation of salinity. So these two we have from our budget equations. Those are pretty straightforward at this stage. We'll talk more about momentum on Thursday, and much more about momentum for the rest of the semester. But I want to focus down here on these two equations and this equation. So this is the internal energy equation, which is the first law of thermodynamics. So the internal energy changes when you apply heating or when your volume changes. So there is a work being done by pressure and changes in volume that changes the energy. So you can think of this either as if you compress a gas, that work is done, or if you change its volume, otherwise you interact with the energy cycle, and that's a bit confusing. Entropy over here also has a heating term. It has a funny dependence on temperature, this heating term, but the entropy is materially conserved. So following the motion of a fluid parcel, the internal energy is conserved if you don't compress and if you're not heating. Following the motion of a fluid parcel, the entropy is conserved if you don't do anything to change the entropy. So this might be mixing changes the entropy, or heating or cooling also changes the entropy with this 1/T. Okay, how many equations have we got here? 1, 2, 3, and this is actually 3 equations because they're 3 different components. So 3, 4, 5. One of those, you can either use one or the other. To be 6. And if you count the number of degrees of freedom we have, 1, 2, 3 velocities, 1 density, 1 pressure, 1 salinity, 1 temperature, 1 entropy or energy, then we need one more equation, and that's the fundamental equation of state. The fundamental equation of state is the internal energy as a function of the density, the salinity, the entropy, or it could be another relationship like this that links these variables together and closes this system, so we have everything we need to know. All right. So we're going to talk a lot about, for the next class, we're going to talk a lot about hydrostatic pressure, but for right now, all we really need to know is that pressure is the weight of the stuff on top of you. And so a short stack of bricks builds pretty quickly to a high pressure underneath, maybe similar to a tall stack of pillows. So the density of what's on top of you affects it, but so too does the height of the thing that's on top of you. So as we go down in the ocean deeper and deeper, we expect the pressure to go up and up because of the weight of the water on top of you and the atmosphere on top of that. Very roughly, the pressure measured in decibars, which is 1/10 of a bar. A bar is 1 bar is roughly atmospheric pressure. The pressure in decibars from the ocean relative to the atmospheric pressure above roughly goes up by about 100 decibars per 100 meters. It's not quite that, so 1 decibar per meter with a relatively small difference. The differences get bigger toward the bottom. But what that means is with depth, the pressure is linearly increasing. But there are also lateral variations in depth. We're going to see these two figures very often. This is a near surface pressure estimate, and this is a pressure estimate at about 1,500 meters. You can see that there's lower pressures here near Antarctica than there are elsewhere. And here you can see these interesting structures that have higher pressure than their surrounding environments at that depth. So, well, we're going to talk a lot about how pressure appears in the momentum equation. Think about that. But for right now, we just want to think about the pressure effect on the equation of state. So how does pressure affect seawater density? So every 10 meters of water is equivalent to about an atmosphere. That's what I just said. Water is relatively incompressible, or liquid water is, I should say. It's relatively incompressible. So the density, but even so, the density due to these enormous pressures can reach about 2% by the time you get to the deep ocean. Increasing pressure also produces this warming. As you go down, you're compressing, and that compression actually does work, which means that you change the temperature. So there's this concept of potential temperature or potential density is what we're trying to get to, which is a way to account for the adiabatic warming. So the warming without increasing the energy in that fluid parcel, but allowing the energy and the temperature and the density to change as it would. So sorry, allowing the energy, keep preserving the amount of energy, but allowing the temperature and density to change as you go up and down is what we're trying to get at with this potential temperature or potential density concept. Okay, so here's an equation of state, which does not actually have much complexity to it. The real equation is extremely complex. So 75th order polynomial is what is the standard right now. But a linear approximation to it is something like this, where the density is equal to some background level of density. If the temperature was equal to its reference temperature and the salinity was equal to its reference salinity and the pressure was equal to its reference pressure, then the density would just be equal to that reference density. But if the temperature changes away, the temperature goes up, the density goes down. If the temperature goes down, the density goes up. If the salinity goes up, the density goes up. If the pressure goes up, the density goes up. And here are the coefficients. I'll give you a whole big table of coefficients later, but this is a nice set to think of when you're just thinking about the basics of how things work. If you plug in what the typical ranges of variability in temperature and salinity are, you get about a 0.6% variation in density because of just the temperature part, about a 0.2 from just the salinity part, and about a 0.4 from just the pressure part. But only 0.0004% for the horizontal pressure changes. So most of the pressure changes are in the vertical, but the interesting ones, the ones that drive fluid motion, are the ones that have to do with horizontal pressure changes. Okay, So we said before that we could have done either the internal energy equation or the entropy equation. The story is even more fiddly than that. But let's write the energy equation and the entropy equation in a little bit different form, and just talk our way through. So the energy is conserved following the fluid partial if the pressure, and oh, sorry, this is 1 over, alpha is 1 over rho. That's the specific density. It's just the inverse of the density itself. 1 over rho responds to heating, or either of these can change as you move around following the motion of the fluid. A different way of writing it is to eliminate the alpha in favor of a compression and times an alpha, which is a nicer way to write this. So these are two different forms of writing the energy equation. The enthalpy is a different thermodynamic property, which is related to the energy and the entropy. The enthalpy evolves following the fluid, but it has a term that depends on changes in pressure of the motion of the fluid. And it also responds to external heating. The entropy is the amount of randomness in the fluid. So it relates to the second law of thermodynamics rather than the first law of thermodynamics. But from our perspective, we only need one more thermodynamical equation to close our budget. So if we assume that all of the changes are reversible, that is, the amount of randomness is not changing as the motion flows around, then we can use entropy and energy interchangeably. They both are expressing the same thing about how the fluid evolves. This form looks even the simplest of all. It doesn't have a compression term, except it has this multiplier by temperature, which does make things a little bit complicated. So, plus there's this term here, which is the rate of change of salinity affects the entropy. The salinity doesn't directly affect the energy or directly affects the enthalpy, but it directly affects the potential, the entropy. So there's fiddly changes here. Okay. We need to make something simpler, or it would be nice if we could make something simpler. So last time I said that the meteorologists actually came up with a way to simplify that made things much easier. And this is how it works in the energy equation. If the energy is the specific heat capacity times the temperature, or the enthalpy is the specific heat capacity at a given pressure times the temperature change, or the entropy is the specific heat capacity at a particular pressure times the log of a potential temperature, then you can write these equations from just plugging into these equations. So let's see what they say. So here is the internal energy equation written in terms of the temperature. And we have a pressure part. Oh, sorry, no, we have switched the order, which is a little confusing. Sorry, this is the one that results from the enthalpy equation. We get a temperature change, we get a pressure change. We have specific heat there. We have the specific volume here. This is the energy equation rewritten from this form. This energy equation, instead of the internal energy change, we're actually seeing that there's expansion at constant volume, coefficient times the temperature. But this is still not that simple because it doesn't depend material on the fluid. We still have this compression term. The pressure equation looks something like this. So this is coming from an equation that we don't even have written down on this page, but this is one that you could extract from this equation as well. Or the potential temperature, noting the way that entropy is defined based on potential temperature. You plug this into the entropy equation and you actually get the potential temperature is conserved following the fluid. So in an ideal gas, the potential temperature equation is the simplest equation out of all of these. So this is the one that atmospheric scientists prefer. So and this is what potential temperature turns out to be. It's the temperature times a ratio of the reference pressure to the actual pressure at which you're measuring this temperature with a coefficient. This guy is maybe easier to solve for because this equation is relatively simple. That's the concept of potential temperature in the atmospheric case. So let's think a little bit about what might happen if we were trying to think about compression and expansion. So imagine that you're going up and down in the water column. You'd have to track the temperature, the density, the pressure. We know that our instruments are extremely limited as to which they can measure those. Even under the linear equation of state, what's changing as you go up and down? Well, the pressure is changing. We talked about that, which means the density is changing. But maybe the density is changing because of the temperature, or the density is changing because of the salinity as well. Or maybe the temperature actually doesn't change independently of the density or the pressure. So when a particle deepens in shallows, the hydrostatic relation tells us the pressure changes. But what else in this relationship changes? Density, temperature, both, all? In the ideal gas case, where there's only temperature, potential temperature, entropy, what changes is that the entropy is conserved going up and down, which means that the potential temperature is conserved going up and down. So the potential temperature doesn't change in an ideal gas as you go from height to height. Then from that, you can figure out what the resulting density, temperature, pressure are. Okay. Why are all these equations tangled up? Well, if you're a real thermodynamics buff, you would know that there are these relationships between the enthalpy, the pressure, the specific density, and the internal energy, the pressure, the specific. So these kind of calculus relations called Maxwell's relations, which tidies up all of this stuff, it allows us to switch from one form to the other in a relatively convenient way. I'm not going to cover too much on this, but I will note that one funny variable out of this is called the Gibbs function, and it's a really useful one for a concept we're going to talk about in a few minutes. Okay, so when we compress and expand, when we go up and down in pressure, both the temperature and the density change. Ugh. But just as in the atmosphere, we can conceptualize the conservation principle for internal energy or entropy or enthalpy or what have you, and then use that to build a concept of potential temperature or potential density that doesn't change when you go in large deviations with pressure. So if we assume that the equation of state holds, got that, we assume that salinity is conserved as we go up and down, and we assume one of three relationships, either that the flow is reversible, which means that the entropy is conserved, or the flow is adiabatic, which means that the energy is conserved, except for work being done by that pressure expansion and contraction. Or we assume that there is the potential enthalpy is conserved, which is a bit crazier one, but anyway, you actually end up with very similar equations from either of these any of these three approaches. They are subtly different in the presence of mixing, as you can see, because in the entropy conservation, we had to neglect irreversible processes like diffusion and viscosity. In the adiabatic sense, we also have to neglect these viscosity, which can sap and diffusion, which can sap the energy. These subtleties are more complicated than what we need to understand. But the point is that because we're operating in a relatively straightforward sense, similar to the ideal gas law sense, we're trying to come up with something that's the simplest version of a potential temperature or potential density that we can use. Okay. So to illustrate this point, Valence goes to a higher level of precision than this simple specific density, or this, we saw this equation in terms of density, which is 1 over alpha. This is just flipping the equation and linearizing it again, which has nonlinear connections between, say, the pressure and temperature, or the temperature and itself. These nonlinear corrections, called the thermobaric corrections, are an important part of the deviations of potential temperature and potential density from what you might expect based on this simple equation, because they connect together the changes in pressure and the changes in temperature. Okay, but let's follow the same approach that we did in the atmosphere, where the entropy was what was used. The evolution of the entropy was taken to be equal to 0, and that's neglecting mixing and diffusion, as we just said, so that the entropy is conserved. In that previous equation, here is the entropy that you would have found for this form of the specific heat capacity, specific density. Here's the entropy that's the equivalent entropy in that equation of state, and it has a piece that depends on temperature, similar to the ideal gas law. It has a piece that depends on salinity. Oh no, getting complicated. And it has a piece that depends on background temperature changes and density changes from the stratification itself in a linearly stratified ocean. This is the pressure piece. Wow. That is a complicated entropy, much more complicated than the ideal gas law entropy. But if you plug this in, then you find a potential temperature equation where the potential temperature is conserved following the fluid in the absence of mixing and heating. And here's what the potential temperature looks like. It looks just like the regular temperature, plus a part that depends on depth, which has to do with the compressibility due to the background hydrostatic approximation. Or you could have written a potential density instead of a temperature, which the potential density looks like the regular density, plus a piece that depends on stratification of the background. And the sound speed is appearing here. It's just shorthand for a set of thermodynamic principles. If the sound speed were infinite, this term would go away and the density would be equal to the potential density. It's because the sound speed is finite. That means that there's a little bit of compressibility hanging around in the fluid, enough to support sound waves, in which case you have to include this compression. Okay, if we put back in the non-conservative terms, the potential temperature equation looks like this, where you have heating with some complicated prefactor that gives you the potential temperature following the motion of the fluid. There is presently a more accurate but similar concept to the potential temperature called the conservative temperature. And it has a slightly different equation set. We can't actually show you even what the conservative temperature is based on those equations easily, but this is the one that depends on the potential enthalpy being conserved that I mentioned briefly. We do not need to use this in our class, but it's maybe something to be informed about as a budding oceanographer. The potential density equation looks like this, where it's things that change the density over here, mixing, heating, etc. And this. I didn't bother to figure out what the coefficient was in this same way, but that's the way it goes. Okay. Either way, whether you're going with the conservative temperature or the potential temperature or the potential density, you've got a thing that's materially conserved following the motion of the fluid in the absence of external forcing. And so you can use it to follow the fluid flow and think about things that are as they go. And remember, it's the key is it's when we go through changes in pressure. So go from shallow water to deep water, that the other terms were triggered. If we just stayed at the surface all the time and didn't change our pressure very much, we could have used regular old temperature. It's the up and down motion of water that really makes the potential temperature deviate from the ordinary temperature, or the potential density deviate from the ordinary density. But that's actually something that happens in the ocean, so we want to be able to think about it. Oh, sorry, repeated slide. Okay, if you want a tiny piece of what that conservative temperature is about, it's about using the Gibbs function, which is a thermodynamic potential function, to derive all of these quantities consistently. So here is an example. If we have the Gibbs function, which here's an approximation for the Gibbs function from Vallis's book, and then we take different derivatives of the Gibbs function, we can find from it the density and how it depends on the salinity and pressure and temperature, or the speed of sound and how it depends on that, or the heat capacity and how that depends, or the entropy, or the enthalpy, etc. So even though so the point of the Gibbs function is that all of these pieces are actually, in a deeper underlying sense, related to one another. So we're struggling a little bit because the exchange of the different thermodynamic quantities is complicated, but really the simple form that we want to get to, something that looks like this, or in terms of the Gibbs function, looks like this, is not, this is easy to use. So we're using a big, powerful thermodynamics to arrive at something that is easy to use. And then we just have to go backwards every so often and figure out what the implications of this transport of potential temperature or transport of conservative temperature is in terms of energy, or something else we might want to know. Here are all of the reference values. So I'll put these are in the slides if you need to look up these things. Okay, so let's think a little bit about what happens if you displace a parcel of water in the vertical. And this is precisely because we want to think about that compression and expansion piece. So if I take this parcel of water at a particular depth with a background potential density stratification, so this is the stratification from light at the top to dense at the bottom, and I offset it, I would find that up here, it would be different in density from its environment. This is the density that we would have expected in the, it would be different in density from its environment. That is, here's the environmental density, but it would have preserved its potential density that it had down here when I displaced it, if I displaced it in an adiabatic isentropic way. That was what we worked so hard to get at, was what would the density be if it was up here? Well, the potential density would be the same as it was down there, because that's the meaning of potential density. It's the one that goes with the motion of the fluid. But now when you find yourself up here, you have a different potential density from your neighbors. You have this one instead of this one. So you might find yourself to be lighter than your neighbors, in which case you would continue moving upward. You would still be buoyant. Or you might find yourself denser than your neighbors, in which case you would sink back down to where you started. So the derivative in this background density gradient, potential density field, how it changes with depth is what determines that stability. This doesn't change its potential density as you go up and down. The background potential density does change when you go up and down. So if you find that the derivative in the background potential density is negative, that means that when you go up here, this would be what? Work our way through. This would be lighter than this, and so this would sink back down. If, on the other hand, the vertical derivative of potential density in the background was positive, then when you go up here with your same potential density, now you would find that this actually had a lower, this would find itself light relative to its environment. And when it is light relative to its environment, it would continue going. So there is, depending on this gradient, a sense of stability to displacements in the vertical or instability to displacement in the vertical. And we frequently rewrite this gradient in this form. We have a negative number and we have a square over here. And that's supposed to imply that, and this is negative. That is, in this case, for the stable case, which is what typically happens in the ocean. If it was unstable, it would overturn and do stuff. So the stable case is the typical. Then with a couple of factors of gravity and density out front, this gives us convenient units. This thing is called the buoyancy frequency, or sometimes the Brunt-Weissela frequency. This n, sorry, not n squared. And so this is the frequency that you would get if you displace this parcel into stable stratification and it oscillated up and down, going back and forth around its initial position. This n is that frequency. And so you can see what that's like. Sorry about the interruption. Okay, so here's an example when potential temperature and temperature are importantly different. If we go up and down from the shallow ocean, or well, not that shallow, 1,000-meter depth, down to 8,000-meter depth in a deep part of the ocean, the potential temperature is stratified with warm stuff up here, cold stuff down the bottom, and doesn't appear to have any unstable regions. The temperature, in situ temperature, on the other hand, actually does have, it looks like it's unstable, but it's not really unstable. That's because the compression effect is so large when you're moving up and down here that the potential temperature correction is needed. So this looks like it's warmer than up here, but if you actually displace this fluid to up there, it wouldn't be warmer because that's what the potential temperature tells you about. This is the same thing, except it's in density, except this is in situ density, and this is potential density. And this funny sigma notation, just to make it even more confusing, is the density when you subtract off the density of pure water from it to make it the part that's variable. Here's the sigma notation. Density minus 1,000 meters squared per meters. No, 1,000 kilograms per meter cubed. Sorry, that should say. Okay. Sound speed. There are variations in sound speed that have to do with that stratification, which is a really interesting part of this whole story. One of the really interesting things is there are channels where the sound waves are reflected back into the channel at mid-depth. That's where whales like to communicate with one another. It's like a telephone channel. It's called the SOFAR layer, and the sound waves that are emitted in that layer can travel all over the world, and whales use this to communicate over long distances. The temperature, salinity, and density variations as a function of latitude look something like this. So we have temperatures. This is the surface temperature, surface salinity, surface densities. You can see that there's some variation. This gives you a sense of the horizontal variations in scale of these different properties. And as we saw in vertical, you get a surface zone and then a picnic line, which is where the density is increasing, or in temperature, the surface zone, and then a thermocline, which is where the temperature is increasing. And then there are these deep zones where the increase is slower. And it's these deep zones that are the ones that are hard to do without this potential temperature correction or potential density correction. You also can have a halocline with fresh water on top of salty water. So either of these ways is the way that you get stratified to a picnic line. It's the picnic line part that talks about the static stability. That's the one that really is important. And we talked about this last time, whether the different salinity and temperatures of the different water masses in the ocean. This is a way of exploring those variations in temperature and salinity with depth and with space. The last thing I wanted to show is just to show you an example of a simulation. So this is a layered simulation with multiple layers, and the wind is driving those layers to move in a clockwise direction. This is just one layer, and you see the water is moving along that layer and then coming back along the western side like this. In the vertical, this water is moving within a potential density surface. So the surfaces of potential density are a guideline for the flow of the ocean. As the ocean flows, it tends to conserve its density. It's not its in situ density, but its potential density, or its potential temperature would also be pretty close to conserved on here, except for the fact that potential temperature and salt combine with each other to set the potential density. So it flows along potential density. It might have variations in salinity or variations in potential temperature. Those would cancel out to arrive at this potential density. The red lines are streamlines for this flow, which is actually an interesting story. That's something called those are the streamlines of Montgomery potential. This guy, Ray Montgomery, was actually a professor at Brown who figured out that the potential function for flow along a potential density surface is something called the Montgomery potential. And so I've just shown those to help guide your eye. If I went to a different potential density layer, one that's deeper, therefore denser, we see a different part of the flow, but a similar kind of pattern in terms of there being flow along that potential density surface. If we go to a really deep one, see something like this. And so this is just a cool thing to think about as we start thinking about why potential density is so important. It's because the motion is conserving its potential density. Looking from the side, you can see that as the model sets up, these interesting lateral variations of potential density are setting up, and the flow is happening underneath this. And there's a surface layer, which also varies in latitude, as this shows. And then here's east-west sections, all kinds of cool stuff happening. This is the kind of thing that we want to try and wrap our head around. The last point that I wanted to make before we stop is that poleward energy transport is actually directly related to the transport of potential temperature. So the poleward energy transport is the density times the energy per unit mass times the velocity, which can be pretty much approximated by the density times the specific heat capacity times the potential temperature. Because you move that water up to the surface reference potential temperature, you move that up to the surface, and then you can exchange energy with the atmosphere. So this paper in 1999 is that. So if you wanted to calculate some of those pieces when we get to the meridional overturning part of our story, you could do it with this simple relationship where the amount of energy transported, the flux of energy, looks like this. Thank you very much. Those two last slides are something else that you can take a look at. They're more complexity than what we need to talk about.